Intro to phasors. So let's say that we have a voltage V of t that is a sinusoidal signal having a magnitude Vm. It's a cosine signal. It oscillates at an angular frequency of omega multiplied by time, and it has some phase angle theta v. And for the sake of argument, let's also look at a current waveform of the same shape. So as a sinusoid, it'll have a magnitude, an angular frequency, and some phase angle theta. These are time domain representations of signals. In circuits 1, we learned that these time domain representations of signals are nothing more than the real part of mixed domain signals, Vm e to the j omega t plus theta v, and the real part, Im e to the j omega t plus theta I. So here's our mixed domain representation, and we got here by using Euler's identity. So Euler's identity states that e to the j x is equal to cosine x plus j sine x, right? So when I say our time domain signal is just the real part of this, it's literally just the cosine part. It's not the part that includes the imaginary operator j, okay? So here is where we are going to introduce the concept of a phasor, okay? So our time domain signal contains 3 pieces of information: a magnitude, an angular frequency, and a phase angle, right? So here's our magnitude, Vm and Im respectively, an angular frequency of omega and omega, and a phase angle of theta v and theta I. Our mixed domain representation, or our complex number representation, contains those exact same 3 pieces of information about our signals. What we are going to observe is that one of those pieces of information is redundant. So if our circuit is only operating at a single excitation frequency, omega, every single signal is oscillating at that same angular frequency. And since it all has that one characteristic in common, we can ignore or suppress that piece of information because it doesn't really do anything for us. And that leads us to our phasor representation. So our phasor representation, which I'm going to put down here, actually I'll put it up here, sorry, would be a phasor voltage V, where I indicate phasor quantities by putting a bar over the top of them, a horizontal bar over the top, because I can't write in boldface. And we'll have a phasor current I, like so. And this is simply a polar form complex number containing the magnitude information and the phase angle information. So we are suppressing that redundant angular frequency information that's common to all signals. So these are our phasor quantities. And we sometimes refer to this as working in the frequency domain. So I'm going to use the terms phasor domain and frequency domain interchangeably. Okay. So one thing that I want to point out here is that our phasor domain uses the cosine representation of our signals as its reference. So in order to go from the time domain to the phasor or frequency domain, we have to express all of our time domain signals as cosines before we can move into the frequency domain. So let's say that I have a voltage VA of t is equal to 6 cosine 13t plus 11 degree volts. What would its phasor domain representation be? Exactly right. So the phasor voltage VA would simply be 6 angle 11 degrees volts. If I had a voltage VB of t that was 8 sine 19t plus 50 degrees volts, what would my phasor domain representation be? So that's incorrect. It can't be 8 angle 50 because we have to shift the sign to a cosine. And we do that by subtracting 90 degrees from the phase end. So it would actually be 8 angle negative 40 degrees. We could. Wait, hold on. No, we can't. Negative 40 would be positive 320. We could if we were so inclined. But typically speaking, negative 180 to positive 180 is the general constraint. So that would give us the positive, or excuse me, the smallest possible magnitude of our angle if we restrict it to lie between positive 180 degrees and negative 180 degrees. All right, one last example here. What if I gave you EC of t were 4 cosine 3 pi t plus 18 degrees minus 2 sine 3 pi t minus 60 degrees. So this is a single signal expressed as a sum of sinusoidal quantities, okay? To do this in the time domain would require the application of a lot of particularly annoying trig identities to remember. So instead, we can do this math in the frequency domain. where we can represent this portion right here by its phasor, which would simply be 4 angle 18 degrees volts. I forgot to include units, my apologies. And we could represent this guy right here as 2 angle negative 150 degrees volts. And we're simply taking the difference of those two quantities. And this is math that I can throw in my calculator and do easily, as opposed to having to apply multiple trig identities and coming back around to not really stumbling into the correct answer, but a lot of work going into it. Yes, sir. Adding 90 degrees is not correct. So if you give me, let's finish this up and I'll explain why adding 90 degrees. Well, so we don't add 90 degrees to go from sine to cosine. In this particular case, we could call it plus by shifting this by positive 180 degrees, which would be the same as adding 90 degrees. But it only works because we have this minus sign out here. So anyway, so 4 angle 18 minus 2 angle negative 150 looks like 5.971 with an angle of 21.993. Yes, sir.
Does that have anything to do with like linear time and variance framework?
All of these are LTI.
Right.
Yeah.
I was thinking that shift is that direction because you want to start at 0 and okay. Yeah. Thank you.
So we're only dealing with LTIC systems in this class. So you could argue that that's the reason that we're using the cosine function as the base, but the easier thing to me is literally just from direct application of Euler's identity, where we're dealing with the real portion of all of our signals.
Pardon me, I just meant the shift from cosine to sine. If you want to keep that consistent, it seems better to have that.
Well, cosine to sine is always 90 degrees, so let's prove it.
No, again, I hate to get lost in the weeds. It's just a theoretical thing that I was curious about. Thank you.
Yeah, so the reason why it's a negative 90 degree shift is because now that my head's stuck on it, we're going to talk about it. They'll suffer through it in quiet indignity. So a cosine function would look something like this, where if I could draw better, things would be potentially more helpful. And a sine function would look something like this. Again, my ability to draw would vastly help things here. Okay. So the sine function is simply the cosine function shifted to the right by a certain amount of time. Because there's a time shift to the right, it has a negative phase angle introduced in the shift. Well, the amount of time shift that we experience here, let's call that delta t. So from here to here is delta t, where this delta t is related to omega radians per second. No, our phase angle phi over omega. Because that's degrees or angle units divided by angle units per seconds, which is giving us a shift in seconds. So obviously, if we wanted to figure out what our phase angle was, then we would simply take omega and multiply it by delta t, and that tells us what our shift is. Well, for a cosine function and a sine function at the same frequency, that shift is going to be exactly pi over 2, or 90 degrees. And then the negative sign is coming from the fact that we are shifting to the right. So to convert, so just, I'm going to write this down. Sine of x, where x is an arbitrary angle that may include a phase angle and all that kind of stuff, is the same as cosine of x minus 90 degrees. So whatever the argument of the sine function is, 3 pi t minus 60 degrees, the cosine is then going to be 3 pi t minus 60 degrees minus an additional 90 degrees, which is how we got this negative 150 there. All right, so I feel like we have a grasp on how to convert from the a time domain signal into the frequency domain. Going the opposite direction is rather trivial. We take the magnitude, we take the phase angle, and we just put in whatever angular frequency we're working at. That's it. So to go from the time domain to the frequency domain is we keep the magnitude information of the cosine function and the phase angle of the cosine function. And that's the information that gets put into our phasor. To go from the phasor back, we simply use the magnitude of the phasor to be the magnitude of our cosine function. The phase angle is the phase angle of the phasor is the same phase angle as our cosine function. And then obviously we need to know what omega is in order to put that in. That has to be given to us. It cannot be in any way, shape, or form inferred from the phasor itself. Okay. So let's now develop phasor relationships for circuit elements. And we're going to start with a simple resistor. So here's our resistor R, and I'm going to say that my voltage drop, VR of t, is occurring like so, positive polarity on the left, negative polarity on the right, and I have some current, IR of t, flowing into the positive polarity terminal, such that my resistor is absorbing power. If VR of t is a sinusoidal voltage, so having a magnitude Vm, cosine omega t plus theta v, and our current IR of t is of the form Im cosine omega t plus theta I. In order to avoid our time domain relationships, we're going to start here in the mixed domain, and then we're going to let our phasor quantities kind of fall out when we suppress our common frequency term. And so that means that I'm going to be using Vm e to the j omega t plus theta v to represent my voltage quantity. And I'm going to be using Im e to the j omega t plus theta I to represent my current quantity. So what's the relationship between voltage and current in a resistor? Not a trick question. So let's organize it to where I don't have to deal with a fraction. V is equal to I times R. Good old Ohm's law, right? So if I substitute in my mixed domain representation here, what this is going to give me is Vm e to the j omega t plus theta v is equal to r times Im e to the j omega t plus theta I. Are we okay with this? Simply substituting in our mixed domain representation for voltage and current into our Ohm's law expression. What I'm going to do now is I'm going to split up these exponential functions, right? So if I have an exponential function that is acting on an argument that's simply the sum of two quantities, that's the same as two exponential functions being multiplied together. So I could call this Vm e to the j omega t multiplied by e to the j theta v is equal to r times Im e to the j omega t times e to the j theta I. And now I can easily see that there is a common factor of e to the j omega t on both terms, in both terms. So I'm going to cancel those guys out. So this guy cancels this guy. And effectively at this point, I'm now working in the phasor or frequency domain because I've suppressed my angular frequency term in all portions of my system, okay? So the result of that is a complex number, Vm e to the j theta v is equal to r times Im e to the j theta I. Okay. So we can make a couple of observations here. The first of which, on the left-hand side, the quantity Vm e to the j theta v contains only my magnitude information and my phase angle information. So that is actually simply my phasor voltage, just written in an exponential form. On the right-hand side, the quantity Im e to the j theta I is nothing more than my phasor current, because it contains only my magnitude information and only my phase angle information. And then finally, I'm left with a scaling factor of R. So this is Ohm's law in the frequency domain. Phasor voltage V is equal to phasor current I times the resistor R. Okay. I'm going to put a box around this guy. We're going to come back and use it in a little bit. We can make a couple of other observations. Okay. So looking at this line above, where I still have the exponential form of my complex numbers, I have an exponential form complex number on the left-hand side of the equal sign and an exponential complex number on the right-hand side of the equal sign, right? So that means that the magnitude of the left-hand side has to equal the magnitude of the right-hand side, and the phase angle of the left-hand side has to equal the phase angle of the right-hand side for those two complex numbers to represent the same quantity. So from that, I can observe that the magnitude of my voltage, Vm, is simply the magnitude of my current times R. And the phase angle of my voltage is equal to the phase angle of my current. So there is no associated phase shift between voltage and current across a resistor. We'll talk about why that is when we get to impedance later on today. All right. So any questions about our phasor relationships for a resistor? Okay. So what we're going to talk about next is an inductor. So if I have an inductor L over which a voltage VL of T occurs and through which a current of IL of T is flowing, if my voltage and current waveforms are sinusoidal in nature, such that VL of T is of the form Vm cosine omega T plus theta V, and IL of T is equal to Im cosine omega T plus theta I. I can again represent these time domain quantities in the mixed domain by using a complex number that contains the same information. So Vm e to the j omega T plus theta V for my voltage, and Im e to the j omega T plus theta I for my current. So what's the relationship between current and voltage and an inductor? There are two, right? I want the derivative based one because, as per usual, I'm going to try to avoid ever using an integral.
The voltage is the derivative of the current times the magnitude of the inductor.
Exactly right. So the voltage drop across an inductor, VL of T, is simply L times DIL by dt. So I'm going to substitute in my complex number representations of my voltage and current here, which is going to give me Vm e to the j omega T plus theta V is equal to L times the derivative with respect to time of Im e to the j omega T plus theta I. This is the real reason why we work in this mixed domain here. Because when we take the derivative of an exponential function like this, or a complex number like this, the derivative operation is simply multiplying by j omega T. Chain rule, right? If we wanted to take the derivative of this function here, the Im is a constant term. So we're taking the derivative of e to the j omega T plus theta I with respect to time. Or only taking a derivative of this portion right here because theta I, or e to the j theta I, represents a constant number. Okay? And the derivative of e to the j omega T is j omega T, e to the j omega T. So again, taking the derivative in this mixed domain is the same as multiplying by a factor of j omega T. If we wanted to suffer through integration in the mixed domain is just dividing by a factor of j omega T, but I don't even like to do that. So this is going to leave us with multiplying by a factor of j omega, not j omega T. My apologies. Yeah, no, that's on me. Yep, nope, that's absolutely on me. That's that lack of sleep thing I was telling you about. So my apologies. Taking the derivative in the in the mixed domain here is multiplying by a factor of j omega, not a factor of j omega t. So j omega L times I m e to the j omega t plus theta I. And I'm going to split my exponential functions up into a product like I did previously. So we'll have Vm e to the j omega t e to the j theta v is equal to j omega L Im e to the j omega t e to the j theta I, suppressing our common frequency terms on both sides yields Vm e to the j theta v is equal to j omega L times Im e to the j theta I. And there's a couple of things we can observe here. Before we get too deep into the weeds, I want to talk about what multiplying by a factor of j out here in the front looks like. Okay. So the reason why I'm making this distinction is because effectively we could treat this term j omega L here as a rectangular form complex number that's being multiplied by the exponential form complex number that is our phasor current, Im e to the j theta. Okay. So what I'm going to do just briefly here is draw a picture of a complex plane. If we went out 1 unit in the real direction, we can simply call this 1, which is the same as 1 plus j0 or 1e to the j 0 degrees, or 1 angle 0 degrees if we chose to go that route as well. Well, if we go up 1 unit in the imaginary direction, this is the same as 1j or 0 plus j1 or 1e to the j 90 degrees. So whenever I multiply by this j out front, that's the same thing as me multiplying by e to the j 90 degrees. Well, if I multiply e to the j 90 degrees times e to the j theta I can make this look like omega L Im e to the j theta I plus 90 degrees. All right, so on the left-hand side, I have a complex number represented only by magnitude and phase angle. So that's the same as my phasor voltage, VL. Then if we're looking at this top representation here, this looks like j omega L times my phasor current IL, or my phasor current is simply Im e to the j theta I. So that's my frequency domain relationship for an inductor. And then, like before, I can observe that the magnitude of my voltage, Vm, is simply omega L times Im, and my phase angle theta V is equal to theta I plus 90 degrees. So the magnitude of the complex number on the left-hand side of the equal sign has to equal the magnitude of the complex number on the right-hand side of the equal sign. The phase angle on the left-hand side of the equal sign has to equal the phase angle on the right-hand side of the equal sign. So these are our relationships for the behavior of voltage and current across and through an inductor in the frequency domain. Any questions about this guy? All right, so our last element of interest then is the capacitor. So here's our capacitor C, over which a voltage Vc of t will occur, and through which a current of Ic of t will flow. If Vc and Ic are sinusoidal quantities, then we'll have Vm cosine omega t plus theta V for our voltage, Im cosine omega t plus theta I for our current. And we could represent each of these signals in the mixed domain as Vm e to the j, omega t plus theta V, and Im e to the j omega t plus theta I. So we do have a derivative-based relationship between voltage and current for a capacitor as well. So let's take that relationship and effectively follow a very similar approach. So for a capacitor, we know that Ic of t is C times the derivative of the capacitor voltage. So we'll have Im e to the j omega t plus theta I is equal to C times the derivative with respect to time of Vm e to the j omega t plus theta V, which is simply multiplying by a factor of j omega. So we'll have j omega c Vm e to the j omega t plus theta V. Once again, we will break up our exponential functions into two portions. So we'll have Im e to the j omega t e to the j theta I is equal to j omega c Vm e to the j omega t e to the j theta V. We can suppress these common frequency terms, leaving us with Im e to the j theta I is equal to j omega c Vm e to the j theta V, which is the same as omega c Vm e to the j theta V plus 90 degrees, using the same identity that we use for our inductor current. So on the left-hand side, we simply have our phasor current IC, and this is equal to j omega c times our phasor voltage VC. equating the magnitudes on both sides of the equal sign, we have Im is equal to omega c Vm. And equating the phase angles on both sides of the equal sign, we have theta I is equal to theta V plus 90 degrees. And so here are our relationships in the frequency domain for the behavior of a capacitor. All right. So what I would like to talk about now is the concept of impedance and admittance. My biggest concern here is that I didn't remember to bring my actual notes for admittance to class. So I'm afraid I might make a mistake. So what we're going to do is we're going to introduce the concept of impedance today, and then we'll start off on next Wednesday with admittance, where I will actually bring notes so that I don't screw things up. Does that sound reasonable? Rajan, do you have a question, sir? Yep, no problem. All right. Our last miniature topic for the day then is the concept of impedance. So for a DC circuit, if we had a linear black box network, with a pair of terminals, and we applied some source voltage Vs across this pair of terminals. If we measured the voltage across our linear black box network and we measured the current flowing into our linear black box network, we found that resistance R of the linear black box network was defined to be simply the voltage drop over the network divided by the current flowing through the network. This is how Ohm's law is experimentally determined. Okay, if we take any two-terminal quantity, so it could be a circuit element, it could be a combination of circuit elements, it could be a material across which we can apply a voltage and measure a current flowing into. The resistance of the material is defined to be simply the ratio of the voltage drop across the material's terminals divided by the current flowing into the material. Okay. Well, in a steady state sinusoidal circuit or a sinusoidally excited circuit, we can develop a similarly defined quantity, which we will call impedance. Okay. So if we take our linear black box network, and we apply some sinusoidal voltage Ds of t, if we measure a phasor voltage across our terminals and measure a phasor current flowing into our material, we can define the impedance Z to be simply the ratio of the phasor voltage divided by the phasor current. So in the frequency domain, impedance plays the role of resistance. Now, since our phasor voltage V is a complex quantity, and our phasor current I is also a complex quantity, impedance itself must be a complex quantity. Okay? So we can express it in two forms, the first of which will be a polar form complex number. So if V is Vm angle theta V, and I is Im angle theta I, then our impedance Z is Vm over Im with a phase angle of theta V minus theta I, or a magnitude and a phase angle. So this is our polar form representation of impedance. Coming strictly from it being the ratio of phasor voltage to phasor current. For our rectangular form representation, we're going to give each of the constituent parts a special name. Okay? So in rectangular form, our impedance Z can be written as R plus JX. Where this R is the resistance, and it represents the real portion of the impedance. The resistance R observed in a DC circuit and the resistance R observed in an AC or steady state sinusoidal circuit literally represent the same thing. Okay. X is what's known as the reactance. The reactance is the portion of the impedance that is associated with energy storage. So it is contributed to by both capacitance and inductance. Okay. So for a resistor, the impedance is given simply by the phasor voltage across the resistor divided by the phasor current flowing through the resistor. Well, 20-ish minutes ago, we literally developed a relationship between those two quantities. So if we go back here, look at this expression in orange. If we divide both sides by phasor current I, that's giving us the impedance. So that we can see the impedance of a resistor is simply the resistor value itself. In a more formal sense, This is R plus J0 as a rectangular form complex number, or R angle 0 degrees as a polar form complex number. So this tells us that for a resistor, we should not expect to see a phase shift between the voltage and current, because the phase angle of resistance is always 0, which is exactly what we observed looking at our complex number relationships previously. For an inductor, we'll have VL divided by IL, which is going to look like J omega L, or more formally, 0 plus J omega L, or omega L with a phase angle of positive 90 degrees. So we see that an inductor does not exhibit resistance. It only exhibits a positive reactance. Okay. Now, this is only true for an ideal inductor. Okay. If we wound a section of wire up into a solenoidal coil, or we wound it around a toroidal core to form a toroidal inductor, we would find that the inductor actually exhibits some small amount of resistance as well. And it's because the inductor is made of wire, and wire has some finite small resistance depending on its geometric properties and the material that it's made of, right? So for a real inductor, we would likely see that the reactance has a much larger magnitude than the resistance. So this would be non-zero but small. This portion right here would be some finite value, and our phase angle would likely be slightly less than 90 degrees, talking about somewhere in the ballpark of 88 or higher. Okay, so not quite 90, but very, very close. Excuse me, that went too far. For a capacitor, the ratio of phasor voltage VC to phasor current IC is 1 over J omega C, which can be expressed in rectangular form as 0 minus J times 1 over omega C, or 1 over omega C with an angle of negative 90 degrees. So a capacitor always exhibits negative reactance. One thing that tends to possibly confuse students here is how I went from positive numbers to a negative sign here. And that's all about 1 over J, right? So as a quick aside here, this will be the last thing that we talk about. One over J is the same as 1 over the square root of negative 1. Do we all concur with that? Well, if I multiply this by the square root of negative 1 over the square root of negative 1, that leaves me with negative the square root of negative 1, which is simply negative J. So anytime I see the reciprocal of J, I can just treat it as negative J because they are literally identical things.
Are J and I the same?
So I want to be clear. When you're referring to I, if you're referring to I as the imaginary operator, the square root of -1, then yes, J and I are the same thing. Yeah, exactly right. The reason why electrical engineers do not use the commonly accepted I as the square root of -1 is because we use it to represent current, and that would be wildly confusing. So we have adopted the nomenclature of using lowercase j for the imaginary operator of -1. I can't think of any other quantity that we use that we use lowercase j for off the top of my head, but I'm sure there is one. In my electronics class, we have 3 different VTHs. One represents thermal voltage, one represents Thevenin voltage, and one represents threshold voltage. And remembering which combination of capital and lowercase letters I'm using to quantify each thing regularly confuses me. So yeah. Anyway, that's for you guys to worry about next year. All right. So this is where I would like to stop for today so that I don't make any mistakes when we talk about the concept of admittance, which is what we're going to kick things off with at the beginning of class on next Wednesday. So we will not meet again until Wednesday of next week due to the Easter holiday. So I hope you all have a great and wonderful miniature break, and I'll see you in a week.